All right, in an earlier video, we looked at trying to find absolute extrema on a closed interval, and we were guaranteed that if a function was continuous on a closed interval, that it would have an absolute max and an absolute min, and those absolute extrema would occur either at an endpoint or at a critical value. Now I want to look at absolute extrema on an open interval, and this idea that if you have only one local extrema, that it actually implies that it is an absolute extrema. And so let's look at this example 3. We've got f of x equals x to the x, and we want to show that it has an absolute extremum on the interval from 0 to infinity. Now we've already looked at this function, and the domain of this particular function is 0 to infinity. So let's take the derivative, and in doing that we want to start by writing it as y equals, because we're going to use logarithmic differentiation here. So we'll write it as y equals x to the x. We'll take the natural log of y. That's going to equal x times the natural log of x. When we take the derivative of both sides, we're going to get 1 over y times y prime equals first times derivative of the second plus second times derivative of the first. When we solve for y prime, we're going to multiply both sides by y, but that y is x to the x. So we're going to get x to the x times, this expression simplified is going to be 1 plus the natural log of x. So I'm looking for a critical value, and I'll find that critical value by setting this derivative equal to 0. But I know that x to the x can never equal 0 because the interval that we're talking about here has an open parenthesis at 0 because 0 is not included. So the first derivative is equal to 0 when 1 plus the natural log of x is equal to 0. I can solve this by saying the natural log of x equals -1. And then I convert this to exponential form by saying e to the -1. So e to the -1 is equal to x, or basically x just equals 1 over e. And so on this one, we have a critical value, and I want to find out if it's a local max or a local min. So this is 1 over e. We're going to use our calculator to help us out here. And so we're going to evaluate. We need some test values. So 1 over e is approximately equal to 0.37 about. So if I want to pick a test value to the left of e, of 1 over e, and I know that my smallest value I can use is 0, right? Because and I can't use 0, but I have to pick a point somewhere between 0 and 1 over e. And so we can choose to test, say, 0.2 on the left-hand side, and we could choose to test 1 on the right-hand side. So I'm going to go ahead and do that. And all we really care about is the derivative positive or negative in here, right? We're trying to figure out if this is a local max or a local min. So I'm going to take 1 plus the natural log of 0.2, and I get a negative value, and I'm going to take 1 plus the natural log of 1. And we know the natural log of 1 is 0, so 1, that's going to be positive automatically, right? We got 1. So I know that it's negative. The first derivative is negative to the left of e and positive to the right of e, so I have a local min. And if I only have one local min, one local extrema, that local extrema has to be an absolute. Because it basically means that the function is not going to turn anywhere but here. And so from the left, my function is decreasing, and from the right, my function is increasing. It doesn't change from increasing to decreasing anywhere else, so you can't have any other local max or local min. So if this is a local min, the function has already turned. It's not going to turn again. It's just going to go up to infinity. This has to be a local min. But let's check it out. I'm sorry, this has to be an absolute min. It's automatically a local min, but it is an absolute min because there's only one. So let's graph that function. Y equals, and we've already looked at this function before, but y equals x to the x. And I'm just going to start with a zoom 0, see what that looks like. Let's do a zoom 6, or let's do a zoom 6. Let's do a standard. And there we go. I'm going to trace on 1 over e. It's supposed to be my, not only my local min, but my absolute min. I hit enter. All right, and that looks like that's my local min. Let's zoom in on that so that we can get a better idea. We can see here my trace again on 1 over e. We can see that that local min is also an absolute min. Right? So again, if there's only one local extrema, that local extrema has to be an absolute. All right, now let's look at what the second derivative tells us about a function. And so we already saw that the first derivative helped us figure out where a function was increasing and where the function was decreasing. And the second derivative is actually going to tell us the concavity and where what we call inflection points occur. Now, if something is concave up, you can think of it as being able to hold water, something like that. It's a little better. And if something is concave down, it looks something like that, and it can't hold water. So what we want to do right now is figure out how can we use the second derivative to tell us the concavity of a function, or the, over which intervals the function is concave up or concave down. So we know that when f is increasing, its derivative is positive. And when f is decreasing, its derivative is negative. And so no matter what type of function we're dealing with, the next derivative will tell us whether the function is increasing or decreasing. So if f prime is increasing, I know that the second derivative has to be positive. And what does that look like? So let's look at when f prime is increasing, what we're basically saying is that the slopes of the tangent lines are increasing. So think about this. When you look at this piece of a function, I've got a tangent line to the left that is negative. I draw another tangent line that's less negative. It's still negative, but it's less negative. At some point here it's 0. It's positive. And as I move to the right here and draw more tangent lines, the tangent lines are getting more and more positive. So what's happening here is f prime is increasing. The slopes of the tangent lines are actually increasing, and that actually occurs when a function is concave up. And so basically, to figure out where a function is concave up, you want to find out where the second derivative is positive. Now let's look over at this concave down, this piece of a function that's concave down. I'm just going to start drawing some tangent lines. And notice my first tangent line is positive, it's steep. The second tangent line is a little less steep, it's still positive. This is less steep, and what's happening is my tangent lines, right, the slope of those tangent lines is actually decreasing. I went from positive, less positive, 0. Now I'm starting into negative, and more steeply negative, meaning a larger negative value. This means that the second derivative, okay, is negative, okay? And when the second derivative is negative, it means that the first derivative is decreasing. So the function is f prime that we're thinking about. It's decreasing, so its derivative is negative. So what ends up happening here is that when your first derivative is increasing, your second derivative is positive. And in this case, that only occurs when you concave up. When your first derivative is decreasing, your second derivative is negative. That occurs when your function is concave down. So in the next video, we're going to look at an example and figure out the concavity of a particular function. And where a function changes its concavity, we call that an inflection point. An inflection point has to occur at a value that is part of the domain.